Organic nomenclature. Organic substances are substances which are comprised of hydrocarbons. Now, hydrocarbons are compounds that contain carbon and hydrogen as their primary elements. They can additionally contain what are called heteroatoms, that are atoms like nitrogen, oxygen, phosphorus, chlorine, sulfur, fluorine, others that are not carbon and hydrogen. A basic hydrocarbon consists of chains of carbon and hydrogen atoms linked together by the carbons, and they form the base for what we call functionalization in organic chemistry. There are separate nomenclature systems for the different classifications of organic substances that are hydrocarbons. If we look at a general breakdown of hydrocarbons, hydrocarbons broadly classify into acyclic and cyclic compounds. Acyclic compounds are those that form a chain whose ends do not link together to form a circle. Cyclic compounds are compounds whose ends will join together and form a ring. Within acyclic hydrocarbons, there are saturated hydrocarbons, which are called alkanes, and unsaturated hydrocarbons, which break down into alkenes and alkynes. Our alkanes will have only single bonds, alkenes will have a double bond, at least one, but no triple bonds, and alkynes will have at least one triple bond. Cyclic hydrocarbons break down into saturated cyclic hydrocarbons called cycloalkanes, and unsaturated cyclic hydrocarbons called cycloalkenes, cycloalkynes, or aromatic compounds. Cycloalkanes, just like alkanes, have single bonds only, but their ends are joined to a ring. Cycloalkenes have at least one double bond, and cycloalkynes have at least one triple bond. There are no cycloalkynes that exist below 8 carbons in length because of the steric strain created by forming the ring. Aromatic unsaturated compounds are interesting because they consist of a ring with alternating single and double bond pattern, where there is no place in the ring that there are 2 single bonds or 2 double bonds next to each other. Now, looking at alkanes, alkanes are called saturated acyclic aliphatic hydrocarbons. That means that they have the maximum number of atoms bonded to the carbons. They do not form a ring. They have electrons that are localized between the atoms of their compound, and they are made up of carbon and hydrogen. There are only single bonds in an alkane. They can either be straight chain or branched, which means that they are all in one straight chain, or there are carbon chains coming off of the main chain. The general formula for an alkane is CnH2n plus 2. An example of an alkane is octane, which has a total of 8 carbons. Now, naming alkanes uses a prefix for the number of carbons with the suffix ane. So prefixes are meth, eth, prop, bute, pent, hex, hept, oct, non, and dec. So for instance, if I had a alkane with 1 carbon, it would be methane. An alkane with 6 carbons would be hexane. We name the compound based upon the base chain of the longest chain. So that is the highest number of carbons in a way that if I move from carbon to carbon, I do not backtrack over any carbons. I can start from either the left or the right of the molecule in naming. For the molecule below, the circled component is the longest chain. If I start from the left, I would number 1, 2, 3, and then 4 before I get to a branch. At that branch, if I go down, I have 5 and 6, which would have a total of 6. If I don't take the branch, I have 1, 2, 3, 4, 5, 6, 7, 8 going from the left. If I go from the right, I have 1, 2, 3, 4, 5, 6, 7 if I take the branch. If I go from the right and don't take the branch, I have 8 again. So the 8 is the highest number and therefore the longest branch. This is then called an octane rather than a hexane or a heptane. A straight chain alkane is called an N-alkane or normal alkane. Beyond a straight chain alkane, the number of possible isomers that can exist where I have multiple configurations gets very high very fast, so we use IUPAC rules to name those alkanes. In naming alkanes according to IUPAC rules, you first name the base chain as the alkane name of the longest chain. The number of carbons, you number the carbons from the nearest substituent left to right or right to left, either way. whichever way the nearest substituent is. The goal is to have the smallest numbers possible on these substituents, or the branch points. Branches are named by the prefix denoting the number of carbons and the suffix YL at the end. So 1 carbon would be methyl, 2 carbons would be ethyl, and so on. The branches are named by the carbon number that they're attached to, and then the name of the branch, separating the carbon number and the name with a dash. For instance, 3-ethyl. The final branch is joined to the name of the base chain. For instance, in the compound 3-ethyl 2,3-dimethyl-octane, there is no dash between the dimethyl and the octane. If I have multiple branches of the same type, I use a Greek prefix like di, tri, tetra, etc. For instance, in this, I would have 2,3,4-trimethyl if I have 3 methyls. If I have more than one branch of different types, I number them in ABC or name them in ABC order, from excluding the multiple branch prefixes. So something like a tri or a di would not be included. I would look at only the name from the number of carbons. So for the compound 2-ethyl, 2,3-dimethyl, 5-propyl, whatever, at the end, I would name ethyl before methyl and then before propyl, because E comes before M, that comes before P. For the compound here, numbering from left to right, I would have 1, 2, 3, 4 before I got to a branch. Numbering from right to left, I would have 1, 2, 3 before I got to a branch. So I would number from right to left. The first branch has 2 carbons sticking off, so that would be an ethyl. At the 4th position, I would have a methyl because there's 1, and at the 5th position, a methyl because there's 1. So there is an ethyl at 3, a methyl at 4, and a methyl at 5. I would name the compound then 3-ethyl 4,5-dimethyl-octane. If I look at this compound, I have a branch at 3, a branch at 5, and another branch at 5. The branch at 3 is a methyl, one of the branches at 5 is a methyl, and another branch at 5 is an ethyl. So I would name this 5-ethyl 3,5-dimethyl-octane. For this compound, going from left to right is the closest substituent. I have at the 2 position a methyl, at the 3 position an ethyl, and at the 5 position a methyl. So this would be named 3-methyl 2,5-dimethyl-octane. Now I can take a name and draw a structure from the name as easily as I can name a structure that I see. The rules for naming a structure, or drawing a structure from the name, for example 2,2,5-trimethylheptane, are to first draw the main carbon skeleton. So I would, with a heptane, draw 7 carbons. From there, I will draw the branches as carbon skeletons as well. There are 3 methyl branches at 2, 2, and 5, so I would put in the 3 methyl branches. From there, I would add hydrogens until all of the carbons have satisfied valences. Looking at several examples of alkanes and their names, we have an 8-carbon straight chain, or N-alkane. In this case, 8 carbons would be an octane, N-octane. Moving to here, we have 7 carbons as the longest chain with a branch at the 2 position that is a 1-carbon branch, so this would be 2-methylheptane. This compound is another 7 as its base chain with a branch at the 3 position, so it would be 3-methylheptane. This compound, again a 7 chain with a branch at the 4 position, so it would be 4-methylheptane. If I tried to add another branch down the road and make 5-methylheptane, it would really just be 3-methylheptane. So one cannot get more than 4 on this particular compound. This compound has a base chain of 6 with a branch at the 3 position that is 2 carbons in length, so is 3-ethylhexane. This compound is again a 6 base chain with 2 branches at the 2nd position that are both 1 carbon, so this is 2,2-dimethylhexane. This compound has 6 as its base chain with a branch at the 2 and a branch at the 3 position that are both 1 carbon, so this is 2,3-dimethylhexane. This compound is a 6 chain with a branch at the 2 and the 4 position, so is a 2,4 dimethylhexane. This compound is, just as before, a 6-base chain with a branch at the 2 and the 5 position, so is 2,5-dimethylhexane. This compound has a 6-carbon base chain with a branch at the 3 position, 2 branches that are both 1 carbon, so this would be 3,3-dimethylhexane. This compound has 2 branches from a 6-carbon main chain, 1 at the 3 and 1 at the 4 position, so this is 3,4-dimethylhexane. This compound has 5 as its base chain, with a branch at the 2 that is a methyl, a single carbon, and a branch at the 3 that is a 2-carbon ethyl. So this is 3-ethyl, 2-methyl pentane. This compound has a 5-carbon base chain with 2 branches at the 3 position, 1 that is a methyl and 1 that is an ethyl. So this is a 3-ethyl, 3-methyl pentane. This compound has 2 branches at the 2nd position and 1 branch at the 3rd position off of a base chain of 5, and so is 2,2,3-trimethyl pentane. This compound has 2 branches off of the 2nd position and 1 off of the 4th position of a 5 base chain, so is 2,2,4-trimethylpentane. This compound has 2 branches off the 3rd position and 1 branch off the 2nd position, all methyls, and a 5-carbon base chain, and so is 2,3,3-trimethylpentane. This compound is another 5-carbon base chain with branches at the 2, 3, and 4 position that are all methyl, so it is 2,3,4-trimethylpentane. And this compound is a 4-carbon base chain with 2 methyls off the 2 position and 2 methyls off the 3 position, so it is a 2,2,3,3-trimethylbutane. All of the compounds that we've just gone through have 8 carbons total, so they're all octane isomers, but the names of the compounds are based on IUPAC rules and vary widely depending upon the arrangement.